Welcome back to another Explainer. Today, we are unpacking a truly groundbreaking 2026 physics paper titled QBism on Locality and Nonlocality. It's authored by John B. DeBrota, Christopher A. Fuchs, and Rüdiger Schack. If you've ever wondered how the absolute cutting edge of quantum mechanics views the very fabric of reality, well, you're in the exact right place.
So here's a question for you. Do we all share the exact same spacetime? Intuitively, of course, you'd probably say yes. You and I exist in the exact same universe, governed by the exact same dimensional rules. But in the quantum realm, this basic common sense assumption is exactly what's being challenged. And honestly, this sets up the central mind-bending paradox we are investigating today.
Okay, let's dive into this. We will cover Wigner's friend and spacetime, rejecting absolute observed events, the personalistic spacetime solution, a purely local interpretation, and finally, the future of quantum gravity.
Section 1. Wigner's friend and spacetime, defining the core terms.
Just as a quick refresher, QBism is an interpretation of quantum mechanics that inherently treats quantum states and measurement outcomes as purely personalistic. Think of it this way. A quantum state isn't some objective, fixed reality just floating out there in the void. No, it's deeply, undeniably tied to the personal observer who is actually experiencing it. And this idea ties directly into the famous Wigner's friend scenario. This is a physics thought experiment involving distinct observers who can actually have completely different quantum measurement outcomes. So Wigner might measure one thing on the outside of a lab, while his friend inside the lab measures something completely different. This right here creates the core problem we have to solve today. How on earth do these two different realities coexist?
To really set the stage, though, we have to look at the Bong et al. No-go theorem. This theorem relies heavily on a traditional physics assumption known as the absoluteness of observed events. Basically, it's the classical assumption that if an event happened for you, well, it absolutely happened for everyone else in the universe. But, as we're about to see, this new research takes a sledgehammer to that exact assumption.
Let's move to Section 2 and see how this builds. Rejecting absolute observed events, a historical progression.
This major shift didn't just happen overnight. If we look back to 2009, QBists were already considering the personalist spacetimes ansatz, an early hypothesis that meshed really well with their highly subjective views on reality. Fast forward to 2021, and we see Cavalcanti laying down some absolutely vital foundational work. That ultimately culminated in 2026 with Pienaar's new pivotal proof, which is exactly what sparked the current paper we're exploring right now.
Now, what's really interesting about this contrast is how QBism entirely rejects that traditional assumption of absolute events. Instead of falling back on the comfort zone of classical physics, it makes a radical shift toward personalistic spacetimes, proposing a highly subjective alternative. Section 3. The personalistic spacetime solution, resolving the paradox. So Pienaar's proof forces this truly shocking realization. It turns out, QBism cannot always assume that distinct observers' outcomes are embedded in a single spacetime. Let that sink in for a second. We literally cannot assume Wigner and his friend share one unified physical theater. Their realities, their actual observed events, are essentially playing out on completely personal stages.
In fact, the authors put it brilliantly in the paper. They write, QBism has no choice but to treat the notion of spacetime every bit as personalistic as it treats quantum states. I mean, wow. It's not just a suggestion or a thought experiment anymore. It's a structural requirement to remain logically consistent and resolve the whole paradox. Ultimately, your spacetime is uniquely yours.
Moving right along to Section 4, a purely local interpretation, making things crystal clear. So the author's main goal with this paper is to finally make crystal clear the sense in which QBism is a purely local interpretation of quantum mechanics. Because of the new theorem showing that spacetimes must be personal, you might easily assume the math gets incredibly tangled. And sure, while the math is complex, the underlying reality is that everything happens locally to the specific observer who is experiencing it. So the crucial point is that this local interpretation remains firmly intact despite quantum theory's age-old violation of Bill's inequalities. By fundamentally making spacetime a personal construct for each individual observer, QBism actually circumvents that famous, spooky action at a distance. It holds its ground against those famous violations and keeps physics incredibly, inherently local.
Which brings us to our final section, Section 5, the future of quantum gravity,
new interfaces.
This extra clarity isn't just about wrapping up old paradoxes with a neat little bow. It actually poises QBism for a distinctly new approach. It connects some vital, long-standing issues at the interface of quantum theory, and frankly, it provides entirely new pathways to tackle the notoriously elusive concept of quantum gravity. By mathematically redefining spacetime as a personalistic experience, rather than just some rigid external container we all sit inside, they are genuinely opening up the very next frontier of modern physics.
So, I want to leave you with this. How will this new, personalistic approach to spacetime rewrite our entire understanding of quantum gravity? If the very fabric of space and time is uniquely yours, how do we eventually stitch all of that together to explain the objective gravity that holds planets in orbit and binds whole galaxies together? It's a massive question. Keep learning, keep focusing on the structure of the universe, and I'll catch you in the next explainer.